Hello and welcome back to graph theory. So we do know that graphs are made up of vertices and edges, but in fact, if we were to apply some constraints on how these vertices can be connected to each other, we can actually have a better time performing certain types of computation. Today we are going to look at certain types of graphs, or in particular a way to restrict connections and graphs that can make our life easier in certain cases. Let's start off something very simple. This graph is in fact a tree. Now we've talked about trees before on the previous episodes, and now we know what it is. And there is a root. This is the root, and there are connections down to more elements, and these elements may branch out further, right? This is the second level. You may not have thought of it this way, but in fact, a tree is a kind of graph. It just happens to be restricted in a particular manner. Now, moving on to graphs. So, graphs can be directed or undirected. That is, when we actually connect vertices with edges, we can actually say this edge only goes in one direction and not the other. Now, what about bipartite graphs? So if you have a set of nodes that you can actually separate into two groups, and all the edges in your graph can go from one group to another, and there should be no edges within the same group. If you can do that, you've got a bipartite graph. So of course, if we have something like this, it's not a bipartite graph. But if you have something like this, even though there is a connection over here, well, there's not a problem because we can actually shift this to the other side. So of course the challenge is, it might look like a bunch of points and lines at first, but it may be possible to shovel things until you get a bipartite graph. So yeah, that's another interesting pattern. Moving on, we have complete graphs, and that is a graph where every single vertex has an edge to every other vertex. So in a very simple graph of these four nodes, this is of course trivial, and well, even if we add one more node, it's still not too complicated, right? But as you can see, as the number of vertices get greater and greater, the number of edges we have to add also get greater. So as you'd imagine, once your graph gets as big as this, if you still want it to be a complete graph, there are going to be many edges. Now we're gonna talk about acyclic graphs. If a graph does not contain a cycle, then it's acyclic. As you can see, now you see this graph is a cyclic graph because I can identify a cycle in the graph. Now if we we were to remove some of the edges, then it will not be a graph, a cyclic graph anymore, because we can't find a path that can make a cycle in the graph. Now, actually, this might be a little bit non-trivial because finding a cycle isn't always gonna be easy, especially if the graph is very large. But just let's just understand the concept that a cyclic graphs can be useful. Now, this one is just as important. If we put together two of the constraints that we've just learned, what we actually get is directed acyclic graph. So because it's directed, and if you see something like this, it may seem like, isn't that a graph? Well, if you really look at the edges, it is the edges are directed, so actually it's not a cycle, right? Now, an edge is called a self-loop if it involves only one vertex. If both endpoints of an edge are same, then it's called a self-loop. We can have a self-loop in both directed and undirected graphs. But the question is, why would we ever have a self-loop in a graph? Well, sometimes if edges are depicting some relationship or connection that's possible with the same node as origin as well as destination, then we can have a self-loop. For example, like interlinked web pages on the internet. It can be represented as a directed graph. Like if a page contains link to another page. So it is very much possible for a web page to have a link to itself. Then we are gonna have a self loop in this graph. Now the next special type of edge that I want to talk about is multi-edge. An edge is called a multi-edge or parallel edge if it occurs more than once in a graph. Once again, we can have a multi-edge in both directed and undirected graph. Now, why would we have a multi-edge? Well, let's say we are representing flight network between cities as a graph. If there is a direct flight connection between any two cities, but then there can be multiple flights between a pair of cities. And therefore, we're going to have a multi-edge in this graph. So I think that's all for now. In the next video, we will be talking about searches in graphs. So stay tuned and don't forget to like, and better yet, subscribe. Thank you and see ya!